Welcome to episode 2 of our production roundtable series. Myself, Evan Clary, and I'm here with Michael Clary and George Mills. And today we're going to be talking about key considerations to create superior gears, the importance of dynamically balancing shafts and cylinders, printing plate mounting systems, and construction and advantage of the serrapid type die mount. So let's get started on the first submission that we had. Key considerations to create superior gears. Dad, do you want to go ahead and take it away?
Yeah, I'll start on if you're evaluating and looking at machines, whether they're new or used machines, to make an assessment. And this is something inherently in the design of the machines, but you can compare and certainly a judgment of overall quality. The greater the surface area, the contact of the gears, the superior the machine will operate. Let's say when we're talking about a conventional spur gear or really any other kind of gear, if the gears are 1 inch wide on one machine and they're 5 inches wide on another machine, it's really kind of a linear thing. It's 5 times more life because you've got 5 times more surface area, or you're reducing the load that much on the individual part of the gear that you're having. And then we get into the whole thing. Once you have the size of the gear, it gets into how it's made in terms of the hardening technique. Is it a ground gear, which is the final surface? And then we get involved in some other types of gears, like helical gears and gears that can be adjusted to eliminate the back. Maybe in terms of at first, George, you want to kick off the various hardening techniques of gears?
Sure. Is a gear can be made on a mild steel and then induction hardened just so that the teeth themselves are hardened. Another way would be to start with a mid-range alloy steel that has, let's say, a hardness in the 30s and still induction harden the teeth. And then the ultimate gear is a gear that is through hardened by drop forging. Drop forging is a rather older technique, but it does yield a superior gear. Induction hardening can take the gear surface up to almost equal a diamond if you want. However, there's the trade-off between how hard is hard and how brittle becomes brittle. But when you look at induction hardening versus what is called gas nitriding only gives you a hardness that's a couple thousandths thick. Induction hardening can go down to, some people take it down past the root of the tooth. It's that much deep hardening on that. I think that's pretty, yeah, that's. And with the induction hardening, what it does is it takes the grains of the metal and actually aligns them to be tougher. Rather than just give them a hardness, it increases toughness. So a lot of the machines are built with induction hardened gears for that very reason.
And I guess a little bit like you talk about that alignment with the kind of ultimately like the forging of the steel is the ultimate alignment and configuration of the molecules within the metal. Because I always liken it to a drop forge as kind of like the biggest, baddest blacksmith ever. And thinking historically, when you had the famous weapon builders of swords and all in ancient days were really aligning using that forging technique, which is an ancient process, but is still the most effective. But induction allows modern technology to emulate some of those qualities in a more rapid fashion.
That's correct.
I've heard you guys talk about slop and gear wear before, and I know that gear wear accelerates as it starts to become pitted and there's already some wear. So your last year of gear life is really accelerating wear very quickly. How can you tell if you have slop in your gears?
Well, if you have two gears that drive cylinders, you can stabilize one of the gears, maybe with a piece of softer material, like even a piece of wood or something, not allowing it to move, and then move the upper cylinder of the gear. And as you feel the gears move, that's what is sloppiness or lost motion between the two. So particularly on a spur gear, it's kind of falling on one side of the gear or the other with how many thousandths or whatever that looseness in the gear is. And that does accelerate wear, but it's also a lack of accuracy in the cylinders together. If those cylinders are, for example, printing or something, you have some lost motion. One way with gears, people use helical gears at times to avoid this because there is not that intermittent contact. There's more of a smoother motion. These are on a helical angle, so they're coming across. So I guess really, George, you get much more contact area, and it's a much smoother regular contact. So the transfer of the load to the next gear is more of a smooth handoff versus a jump handoff, if you would have it.
Well, that's correct, is because many times, depending, as you point out earlier, on gear thickness, you will have the tail edge of one tooth set still engaged when the lead edge of the next tooth set wants to pick it up. And it just becomes this constant rolling type action to the
So,
gear rather than a high speed cog that you would get out of a spur.
so in other words, the two gears are never out of contact with one another. By the time the one gear surface is leaving, the new one is picking up. So it's a smoother motion. And then also, Evan, you get into gears are made in what we call anti-backlash. There are different concepts of doing it. Some would be the gear is kind of basically split in half, and the gear can be adjusted to overcome that lost motion. So one side is tweaked against the pressure of the backside to allow that to happen. So, but that's an age-old thing to try to do that, because once you have backlash and it starts getting severe, the deterioration of the gear accelerates very rapidly, and the performance of the machine deteriorates very rapidly.
Yeah, that's when you start to lose registration in the print section and things like that.
Correct. Correct.
All right. Well, let's move on to number 2, the importance of dynamically balancing shafts and cylinders. And I find this to be interesting because I know that dynamically balancing shafts and cylinders is popular in a lot of industries, and it's been done some in the corrugated industry, but I don't think it's as common in our industry as others. So what is the process to start? What does the process of dynamically balancing look like?
Well, George, maybe describe that. You've been involved in a lot of machine shops on doing that. What does it look like from the aspect of big shafts? We've all seen them balance tires, and we know the effect of a car tire out of balance, but maybe describe the balancing of the shaft.
Think of it this way. Think of a large lathe, and the headstock of the lathe has sensors on it. The tailstock of the lathe has sensors on it. And you install the piece part, you spin it at a known RPM, typically a multiple of the design RPM for the machine, and it will tell you on a printout that is hooked to a computer exactly where any imbalance may be. An imbalance is not a quality issue as such in the making. Things just don't make up perfectly on center. When you're welding things up or cutting keyways, it changes. So it tells you where you're out. I may be out 4 ounces at 120 degrees from the keyway, and therefore it can become a corrective action. Do I want to put equal weight on the opposite side, or do I want to machine some lightning holes exactly where a dynamic balancer tells me that it sees an imbalance?
Well, and I
So
think
the entire objective is to get everything to run smoothly so that it reduces wear long term.
exactly. Not only reduces wear, Evan, if you think about it, the most obvious place is, let's say, a print cylinder with printing plates. And we all know that you can make shafts very stiff and sturdy, but they all have, over the span of a press with this wide cylinder, there is some deflection. And maybe it's, very minimum, but there is some sag to the cylinder. Well, any out of balance condition accelerates that process. So something like printing, going to have a heavy side and a low side, and it's kind of like a tire thumping. As it goes over, if the printing plate is mounted on the heavy side of the cylinder, you would tend to get more impression. If it's mounted on the other side, you would get less impression. So that whole concept is showing up in other things like feed rolls and things like that, or transfer rolls. But the printing is the most obvious place because we're trying to get kiss impression and the minimum impression to transfer the ink. So we would really see those things in that area. Other things are not as dramatic, but even though you don't see them, they're putting pressure on bearings and other things in your machine that are causing premature wear.
Let me ask you a question. Let's compare a mini versus a jumbo on the subject of shaft deflection. Are you more concerned about shaft deflection in, let's say, a jumbo press that's 88 by 200 versus a mini machine?
Well, the answer is really yes. Yes and yes. Because I'm not avoiding the question, but all machines you're concerned about deflection. Because the mini machine, you're trying to make everything small and all to accommodate small boxes. So you tend to make it as tight and as small as possible and still meet the minimums. On the big machine, you may not be so concerned about this, but you just have big shafts, but you're handling heavy duty boxes, maybe triple wall, heavy die cutting and all. And so George can speak to it better than I can, but engineering wise, you run the numbers mathematically. We keep track of building corrugated machines in terms of shafts and deflection in those. And you're really looking at a situation of how do you minimize that deflection, because you've got to be careful, because somebody would say, well, I'll build that big print cylinder and I'll make it out of solid steel, and so it's really strong. Well, you're going to create a bigger deflection because you've got the weight of the cylinder itself is working against you. So therefore, we make hollow or tube construction type print cylinders to reduce the weight, because you don't really give up the strength by having that tube, but then we have to be concerned about wall thickness and other things. So maybe you can comment on more of that from the engineering analysis, George, but you really look at how do you optimize that condition, but balancing is another important component of it.
Well, I think, Michael, you've actually described it very, very well. You want to get the maximum stiffness you can get in the area that you have. Length can be a killer. Years ago, just a quick war story. Years ago, a corrugator supplier made a very, very good corrugator, 87 inches wide. He tried to build 110. He didn't change anything other than stretch it. He only made 3. And that was it. He had to go back to the drawing board and decided it wasn't worth it. Because it's exactly what you say, Michael. You got to go back and you got to reanalyze things. And while you may think diameter helps, it does. At the same time, if it can hurt, because there's a massive amount of weight coming in that creates this natural deflection. And natural deflection could be only 4 thousandths or so. But you add that to an unbalanced roll, and now I think you used the word, it goes thump.
What's interesting, George, you'd say that about somebody stretching something, an anecdotal story about the industry. There was a friend of mine, and he had worked with several of the major manufacturers in the US from time to time at machines. And at times, all manufacturers have tried to make their machines wider and what shafts do they choose. And some of these experiments have been effective and some less effective. And it was very interesting because he showed me an old notebook. And this old notebook had all the incidences of these different manufacturers, their engineering department, stretching machines. And it would give the shaft diameters and the various characteristics. And out to the right of it, there was a little indication, yes or no. No meaning this was not a successful stretch. Or it was good. And the interesting thing is, and you're very knowledgeable on this, is it's a very difficult mathematical calculation to totally predict that deflection. Somebody can say, well, that's fine, you've got a shaft, but then particularly like slotting shafts and things like that, you're putting other loads on those things with carrying heads and yokes and running board through it. So it is not a simplistic calculation. We can certainly run the numbers and get it, but experience tells us a lot too.
That's correct. Absolutely.
Well, very good. Let's move on to the various printing plate mounting systems that are available now that have been used. And the three that come to mind are the Annan System, the Matthew System, and then magnetic plate mounting systems where you can slug in too. You guys want to start with the magnetic system?
Well, I think, Evan, you rarely see that now. It was very popular a number of years ago, particularly with a couple of the big integrated groups here in North America. And so it was really an idea to get quick mount being fast. And it worked well in that thing. The big drawbacks is really two. Number one, plate storage was difficult because this metal material that the plate mounting was made of could get a crease or get damaged very easily, just difficult to store in general. And then the big print cylinder, if you have had it, is a big magnetized magnet all over it. First of all, the cylinders were very expensive to buy. And then secondly, which I think was the greatest nemesis, if the maintenance guys were in the plant and low B, they dropped a bolt or a nut or something in the machine or any type of metal Allen wrench or something and didn't find it, it's attached to the cylinder. And then the next thing you know, they're running it through the machine. So they ended up really coming out of favor because of those reasons.
Yeah, I've only seen a few of those in my experience going through plants. Doesn't seem like they're too popular anymore. George, you want to discuss the Annan plate mounting system?
Well, the Annan plate system is actually your mylar is the full circumference of the cylinder. It has a lead edge hook. It has a tail edge hook. And there's no stretching, there's no pulling sideways. The combination of the two edges will line up parallel and square. And then the actual tail, if you think of sort of like an older window shade roll-up kind of idea, is it can be cranked into tension, or some systems exist today where it actually self-tensions to a known tension so that you're not distorting the mylar backing. So you wind up with a mylar that is the full circumference of the cylinder, and then the various plates are put in, slugged in, whatever term you want to use, to make up the entire unit as one piece. It's rolled.
Motor to self-tension that Annan system?
What was the question, Ann?
Did they use a motor to self-tension that Annan system that you mentioned?
A small servo motor is possible to tension it. It's set up that the motor develops a certain amount of torque, and then it just simply stalls. So you can tell it to pull on the tension, torque, mathematically related. So you can put in the desired tension, knowing that you're not going to rip off the T slot, knowing that you're not going to rip off the tail edge slot.
Yeah, in the early days, Evan, they were all just a manual ratchet, but those systems have been improved, and certain manufacturers offering those servos, as George described.
Now,
Yeah, it's nice to be able to crank it to a predetermined tension every time. You get a lot of consistency if you can do that.
That's right. And the Annan system, we call it Annan because the American guy that made them was the company name was Annan. That type of technology has always been used. I call it minor in the North American market. You get into the global market, and that technology is used almost all over the place.
Kind of interesting, George. It developed here, and then it has grown, and it dominates most of the other major markets, but it is diminished because in North America has gone more to the Matthews system.
That's correct. Yeah, that's the point, is the rest of the world pretty much likes what the Annan system does for it.
I think in a certain way, there's some movement back in North America back toward the Annan, because particularly with thinner backing, thinner plates, the idea of getting the preloading of the pressure of mounting this and kind of securing it to the surface with a known pressure is very desirable, where the strips on the Matthews is kind of what the elasticity of the band, and is my band still have a lot of stretch to it, or is it a long band or a short band and everything?
Yeah, the point there is it takes the operator variableness out of the equation.
Exactly.
It's just consistent time and time and time again. Operator can be good, but if he's got old bands that are stiff, or he just didn't have his Wheaties for breakfast, it might show up as a production variation.
That's a nice thing.
There's a lot of good machine operators out there, but we always want to try to eliminate as much operator black magic as possible so that we can increase consistency from shift to shift, from run to run.
And too, another point is thinking about it, as George said, that the little kit clips with the bands on it is just another thing the operator does not have to take into the machine in loose pieces, where the Annan is just the plate and the two grooves.
Yeah, it seems like a good system. If they do use a wrench to tighten the plate on the Annan system, are there any things where they can mount that wrench to the machine?
I've never seen that, but I guess you could. You know, it's always good to have a home for any device that you would use like that, because again, you don't want loose things laying on top of the machine guard or something that could vibrate and fall in the machine. So that would be good. I think newer machines, most of them have the servo driven with the torque limiting device, which is good. So you're not over tensioning the plate.
The reason I asked that, and leading into our next question on the serrapid type die mount, I've seen machines where you can take the serrapid handles and actually mount them into the machine so that the machine knows that the handles are there when you're starting up.
Right, that's good. Yeah, loose tools and things in a machine are very problematic.
It seems like it, especially going back to the magnetic print cylinder. You know, that seems like that was obviously an issue for the magnetic print cylinder. But shifting to the serrapid type die mount, what do you think a list of advantages would be for that?
Well, I think there's a glaring number one is quick order change. That's number one, number two, and number three all combined.
What's the big, you know, I guess it would probably take about 15 minutes to mount a classic die with bolts, and it takes 2 to 3 with a serrapid type die mount.
The conventional system, it just depends on how big the die is and how many bolts you have to put in, but thinking an advantage, and it certainly, as I say, the first few advantages are all quick setup. But the other thing is you don't have all these bolts in the machine, and we're just talking about loose items in the machine, because the conventional system, you've got all these bolts and people tend to have them laying around on guards or on the top of frames or something like that, all creating a potential problem.
George, what do you think about the construction of this serrapid system? I know we were talking earlier, you said it was kind of like a car valve with springs.
That, Evan, is actually a perfect analogy that it is set up. Anybody that knows how a internal combustion engine is done and the valving is done is, if you think of the serrapid, I think people call them mushrooms. I think if you think of the serrapid mushroom as a car valve, you begin to understand exactly how it works. It goes up through a clearance hole. The die board's rotated, very small distance. The air is then changed state, and the mushroom pulls back into the cylinder with a known force that will pull the die board tight and keep it there the entire operation. Just ready to be released and taken off in a matter of what could only be 15 to 20 seconds when the time comes.
Evan, another thing maybe to point out that as George is describing that spring, it's important, particularly for people who have not tried that yet and are considering it, to think about how it works and maybe concern of how this mechanism is going to secure the die and be a safe situation and not a liability. That will it release the die during operation or something? These big heavy duty springs are in the fail-safe position, because it would be very easy to have the air pressure operate the mushroom hold-downs in both directions, but the air only operates to release the die, and these heavy-duty spring loads hold the die in place. So therefore, if any reason why you're running the machine, you lost air pressure, absolutely nothing happens to the die board and the secureness of it.
Yeah, that's good to know. Safety is important. And then I guess another consideration would be, if you're buying a machine that has serrapid on it, or you're thinking about doing that, then you need to start thinking about die conversions to the serrapid system. And I know that some people might be interested in just buying all new dies, depending on how old they are. But I also know that Randy Banks, who's the Serra rep here, can convert some dies with what he calls the Serra jig.
Well, that's true. The other thing to think about that, Evan, is if you are considering and you initially go to a serrapid system, it's not all or nothing, because most manufacturers that use the serrapid system on their machines now, they also have the cylinder drilled for conventional bolt hole mounting. The reason for this is, if you felt you should, you can put a bolt or two in it if you were concerned about some die. The other thing, which is not really required, but what you can do is, let's say you were running a job for another customer or another box plant just to help them, or they had a machine that was down, they're probably not going to have a serrapid die that can fit your cylinder, so they would have a conventional die. They can send it over and you can still bolt it to your serrapid cylinder, because the conventional holes are in there. The other consideration is what you said: if you buy it and then you convert the dies. And we all know you've got some die stored around there that you haven't used in months and months and months. You're not sure you're ever going to run that job again. Maybe you don't want to throw it away just in case you get it. So you may not want to convert all those dies until you really had the need, or they show some frequency of operation, and you can still mount them in a conventional fashion.
Sure. It's like the 80-20 rule. 20% of your dies you use 80% of the time.
Correct. Precisely.
Well, very good. I think these were some interesting topics today. Thank you, everyone, for joining us for episode 2 of our production roundtable with Michael Clary, George Mills, and myself, Evan Clary. If you have any questions, please feel free to email me at eclary@ncm-jsmachine.com, and we'll be sure to cover your questions during our next meeting. Thank you.
Thank you.
Thank you.